The topic for this lesson is capacitors in series and parallel. First, we will discuss capacitors in series. In the figure shown, capacitance C1, C2, and C3 are connected in series. When switch S is closed, the capacitors are rapidly charged by the source voltage E. The momentary charging current will be the same throughout the circuit. Thus, at the conclusion of the charging phase, each capacitor must store the same charge, Q. The capacitors are charged by electrostatic induction, since there is no electron flow through dielectric. V1 is equal to minus Q divided by C1, V2 is equal to minus Q divided by C2, and V3 is equal to minus Q divided by C3. Using Kirchhoff's voltage law, we find that E plus V1 plus V2 plus V3 is equal to 0. Thus, E is equal to Q divided by C1 plus Q divided by C2 plus Q divided by C3, or Q times the quantity 1 over C1 plus 1 over C2 plus 1 over C3. If the total equivalent capacitance is C sub t, E is equal to Q divided by C sub t, and 1 over C sub t is equal to 1 over C1 plus 1 over C2 plus 1 over C3. For n capacitors in series, 1 over C sub t is equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus 1 over C sub n. Although this is the familiar reciprocal formula for parallel connection of resistors or inductors, this is a series arrangement. Thus, connecting capacitors in series will reduce the capacitance. Since E is equal to Q divided by C sub t, and Q is equal to C1 times V1, and C2 times V2, and C3 times V3. V1 divided by V2 is therefore equal to C2 divided by C1. Thus, E is equal to Q divided by C sub t, or V1 times C1 divided by C sub t. As illustrated, the other voltages can be developed similarly. And V1 is equal to E times C sub t divided by C1, and again similarly for the other voltages. If n series capacitors all have the same capacitance C, then C sub t is equal to C divided by n. For two capacitors in series, C sub t is equal to C sub 1 times C sub 2 divided by the quantity C sub 1 plus C sub 2. V1 is equal to E times C2 divided by the quantity C1 plus C2, and V2 is equal to E times C1 divided by the quantity C1 plus C2. Now let's discuss capacitors in parallel. Considering the circuit shown where capacitors C1, C2, and C3 are arranged in parallel across the voltage source E. Since the capacitors are different, the individual charges are not the same, and thus Q1 is equal to C1 times E, Q2 equals C2 times E, and Q3 equals C3 times E, or Q1 divided by Q2 equals C1 divided by C2, and Q2 divided by Q3 equals C2 divided by C3. The total charge Q sub t can be determined by adding the charges in each of the capacitors. Thus, Q sub t is equal to Q1 plus Q2 plus Q3, or C1 times E plus C2 times E plus C3 times E, which is equal to E times the quantity C1 plus C2 plus C3. If C sub t is the total capacitance, then Q sub t is equal to E times C sub t. Thus, C sub t is equal to C1 plus C2 plus C3. For n capacitors, C sub t is equal to C1 plus C2 plus C3 plus C sub n. This is the familiar series formula. Thus, capacitors in parallel increase the total capacitance. When n parallel capacitors all have the same value of capacitance, C sub t is equal to n times C. Let's look at an example. In the circuit shown, C1 is equal to 30 microfarads, C2 6 microfarads, and C3 is equal to 3 microfarads. E is equal to 64 volts. Calculate the values of C sub t, V1, V2, and V3. What are the amounts of energy stored in each capacitor? Since the capacitors are in series, the total equivalent capacitance, C sub t, is equal to 1 divided by 1 over 30 plus 1 over 5 plus 1 over 3, which is equal to 1.875 microfarads. The charge stored in each capacitor is determined by Q equals C sub T times E, or 120 microcoulombs. The voltage is V1 is equal to Q divided by C1, or 4 volts. V2 is Q divided by C2, or 20 volts, and V3 is equal to Q divided by C3, or 40 volts. The energy stored in the 30 microfarad capacitor is determined by the equation W1 is equal to 1/2 times Q times V1, or 240 microjoules. And similarly, the energy stored in the 6 microfarad capacitor is W2, or 1200 microjoules. And the energy stored in the 3 microfarad capacitor is W3, or 2400 microfarads. Note that the highest value of capacitance stores the least amount of energy, and vice versa. Total energy stored, W sub T, is equal to 240 plus 1200 plus 2400, or 3840 microjoules.